In this lesson, we're going to look at tangents, arcs, and chords, and a few of our first theorems with circles. So we're going to fill in these blanks for the theorems, and then in the next examples, we will work out some problems that use these theorems. So the first theorem is theorem 10.1, and it says, in a plane, if a line is tangent to a circle, then it is perpendicular to a radius. So the way that we can check for this to see if this is perpendicular is to see if that's going to be a right angle. And so what we're going to do to figure out if this is a right angle is we are going to pull from our right triangle knowledge and figuring out if something's a right triangle, and we're going to create a triangle and figure out if that's a right triangle to figure out if this is a right angle. So that's how we can use this theorem to figure out if something is a tangent line. So a tangent line is perpendicular to a radius at the point of tangency. The next theorem is 10.2, and it says in a plane, if a line is tangent to a radius of a circle at its endpoint on the circle, then the line is tangent to the circle. So this is kind of the converse of the previous. So if a line is tangent or is perpendicular to a radius, so if a line is perpendicular to a radius of a circle, then it is tangent. So that's the converse of theorem 10.1. Our next theorem says if two segments from the same exterior point, so exterior just means outside of the circle, so if two segments from the same exterior point are drawn to the circle, so we would look at the point of tangency to the circle, then the segments that are created are congruent. So these two distances, the distance from that exterior point to the point of tangency of these two segments would be congruent. So now let's look at some theorems that are going to use these. So for example 1, we have our question, is segment CE tangent to circle D? So we're going to figure out if this is tangent. So what we need to know to answer this question is going to be, is CE tangent to a radius? So what we're really asking is CE perpendicular to the radius DE? So I want to know if this is a right angle. So is this a right angle? So to figure that out, what I'm going to do is I'm going to classify this triangle DEC. So to classify a triangle, what we do is we compare the square of the longest side. So I'm going to do 45 squared. And I'm going to compare that to the sum of the squares of the other two sides. So 11 squared plus 43 squared. So these are some pretty big numbers. I don't know off the top of my head what the square of 45 or what the square of 43 is. So I'm going to pull up my calculator. And I can type those in. So 45 squared is 2,025. I know that 11 squared is 121, but I don't know 43 squared. So 43 squared is 1,849. So I'm kind of comparing these values. So I'm going to do 121 plus 1,849, and I get 1,970. So 2024 is greater than that, and therefore this is not a right triangle. By classification, this is going to be a obtuse triangle, but it's definitely not a right triangle. So whenever we're answering this question, we would say segment CE is not tangent to circle D because I'm just going to try to block my work off out of this, because CE is not perpendicular to radius DE. So since it wasn't true that the segment was perpendicular to a radius, then it's not a tangent. So this is no. All right, next we're going to look at these two segments, and it says that segment AB and AD are tangent to circle C. So B and D are points of tangency, and A is a point on the exterior of the circle. So what we're going to do from here is we are going to look at this last theorem that we talked about, 10.3, and it says if two segments from the same exterior point, A, are drawn tangent to a circle at B and D, then the segments are congruent. So since those segments are congruent, and so just thinking back to our proofs and how we know these things, we're not writing a proof right now, but it is kind of part of our life now. So since they're congruent, I know that those two things are equal. So I'm going to set their measurements equal to each other. So I'm going to have x squared minus 4. That's the length of AB, and that's going to be equal to AD, which is 21. And then I'm going to solve this equation for x. So to do that, I'm going to add 4 to both sides. And then I get that x squared equals 25. And I'm trying to find the value of x here. So to do that, I do the square root. And if I take the square root of 25, I get 5. So that is true. 5 is going to be a solution, but we also have to think about in an equation like this, what other number could also give us a square of 25. So another thing, because 5 squared equals 25, if I take the inverse of that, negative 5, that would also give me a square of 25. So in this case, I test it. It works because it doesn't give me a negative number as a side length. So for this one, I can say that that is 5 or negative 5. Sometimes the negative version won't work if it gives you a negative side length, but in this case, both of those answers work. And I can check that by plugging them back in and making sure that it's equal. So if I plug it back in, 5 squared and negative 5 squared give me 25. And then if I subtract that 4 from both of them, I get 21. So both of these numbers work in this situation. All right, so let's look at some more theorems here. First, we're going to look at the relationship between the minor arc and the central angle. So the measure of the minor arc is equal to the measure of the central angle. So if we have an angle that comes from the center of the circle, that measurement is going to be the same measurement as the measure of that minor arc. So if you think about going around that center point of the circle, you're going to have 360 degrees on the inside of the circle. That whole circle is made up of 360 degrees as well. So the total sum of all arcs that create a circle should be 360 as well, and therefore the central angle is equal to the minor arc. So the next thing we have is the arc addition postulate. Very similar to our angle addition postulate and our segment addition postulate. This says the measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. So if you have two arcs that are side by side, you can add those together to find the measure of the arc that contains both of them. All right, so next theorem here is 10.4, and it says in the same circle or in two congruent circles. So congruent circles would have the same radius. So in the same circle or in two congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So here we have chords that are congruent. They don't necessarily even have to touch the same point. These do, but they don't have to. So if I put some letters on this, A, B, and C, so what I can see is that those two chords are congruent, and those are segments. So segment AB is congruent to segment AC. And with that being true, this is an if and only if, so it's biconditional. It goes either way. So if those chords are congruent, then those arcs that are formed are also congruent. So arc AB is going to be congruent to arc AC. So let me put that in a different color just so that we can see that comparison and what we're talking about. So AB and AC are segments. If I'm talking about the arc AB, I am talking about the part around the circle that goes from A to B, and arc AC is the arc that goes from point A around the circle to point C. So those two arcs would be congruent if the two chords are congruent, or the two chords are congruent if the arcs are congruent. All right, our next theorem says if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So if it's perpendicular, then it's going to bisect the chord, which let's put some symbols, some notation on it again. So this is chord AB, and it's intersecting at point D. So the chord is going to be bisected, and that's going to be the segments. AD is congruent to DB, and the arcs that are created are congruent. So arc AC is going to be congruent to arc CB. So if that diameter is perpendicular to a chord, then both the chord and the arcs are congruent. All right, our next theorem is 10.6, and it says if one chord is a perpendicular bisector of another chord. So here, if one chord is a perpendicular bisector of another chord. So we have one chord that has been bisected, and it's perpendicular. So if one chord is a perpendicular bisector of another chord, then that first chord is a diameter. So in order to bisect, it would have to go through the center of the circle, and that's going to make it a diameter. All right, theorem 10.7 says in the same circle or in two congruent circles, two chords are congruent if and only if they are equidistant from the center. So let's throw some letters on this again. So in order for this to work, two chords are congruent if and only if, so two chords AB and CD are only congruent if they are equidistant from the center. So remember that distance is always measured perpendicular to what you're measuring. So these chords have to be perpendicular to that segment that's coming from the center. And if that's true, then those are congruent chords. All right, so we're going to use these different theorems to solve different problems here. So first, let's look at this diagram and figure out what we know. So from this, I know that A is the center of the circle. So I'm going to say that A is the center of the circle. So if A is the center of a circle, then BD is a diameter. Another thing that I know is that since A is the center, angle CAD is a central angle. And so if I think to that very first thing that we talked about at the top, it said the measure of an arc is equal to the measure of the central angle. So if I look at angle DAC, and that measure is 148 degrees, then the arc is also going to be that same measure. So looking at the arc that connects those points C and D, so the arc that runs from C to D is going to be 148 degrees as well. So the first arc that we found is the measure of angle, nope, not angle, arc CD is equal to 148 degrees. All right, so if we know that BD is a diameter, then that's also a straight line. So another thing I can do is I can think about this straight line and what has to be left over here if angle DAC is 148 degrees. So a line equals 180 degrees. It has a total sum of 180 degrees. So these would be a linear pair. So to figure out the measure of that other side, that other angle, I am going to do 180 minus 148. So the remaining side, the remaining angle over here is 32 degrees. So the measure of angle BAC is 32 degrees. That means that the measure of arc BC will also be 32 degrees. So the measure of the next arc, which is BC, is also 32 degrees. So altogether, if BD is a diameter, then that means that this other part, this arc that goes from B to D, is a semicircle. It is half of a circle. So if a whole circle is 360 degrees, then the measure of arc BD is going to be half of that. So half of 360 is 180 degrees. So the measure of arc BD is 180 degrees. Since that's 180 degrees, if we look at the other side, if we name it BCD and go the other way around, that would also be 180 degrees. So it said find the measure of each arc, and we can do that by finding the sums. All right, here is our next example. So on this example, what I see is I see congruent chords. So from this figure, congruent chords show up. And those congruent chords are chord BD and BC. So those are segments within this figure, and those are congruent chords. So congruent chords have congruent arc lengths. So if BD is congruent to BC as segments, then as arcs, those will also be congruent. So arc BD will be congruent to arc BC. So looking at here, BD, the arc, will be congruent to BC, the arc. So anytime things are congruent, then their measures are equal. So the measure of arc BD will be equal to the measure of arc BC. And that's from this theorem about congruent chords, 10.4. So this goes with theorem 10.4. All right, so using that, I'm going to plug in things that I know. So the measure of arc BD is given by the expression 3x plus 11. And the measure of arc BC is given as 2x plus 48. So here's an equation I'm going to solve, and I'm going to solve it for x. So the first thing I'm going to do is move an x value. So I'm going to subtract 2x from both sides. And then I have x plus 11 is 48. Then I'm going to subtract 11 from both sides. And x equals 37. So this is the value of x. I want to make sure that I'm answering the correct question, but the question tells me to find the measure of arc BC. I don't have that yet. So for the measure of arc BC, I'm going to plug this value in to the expression that matches with that. So this is going to be 2 times 37 plus 48. So as I solve through this, I want to make it in simplest form. So 2 times 37 is going to be 74, and then 74 plus 48 is going to give me 122. So the measure of arc BC is 122 degrees. So we do want to make sure that we are solving the question that's asked. All right, in our last example here, we have used the given information to find the value of x. So I am looking just for x on this one. So what I'm given is that AB equals DE, which equals 10. Since there's no markings on that, I'm going to assume that it is talking about the chord. So the chord AB is congruent to DE, and both of those are 10. So this entire length is 10 on both of those. A radius is 6 units. So any radius that is drawn from the center to a point on the circle is 6 units. So I do see that this radius is part of a diameter. And remember that a diameter, any diameter, is perpendicular to a chord. So since the radius is part of a diameter, and I'll just write that down. So radius is part of a diameter. So these little pieces that are coming from the center, I'm going to assume that both of them are perpendicular. So since I'm not really using the entire radius, I don't know that for sure, but I am going to assume that these are both perpendicular because one was marked. All right, so another thing is that whenever a diameter bisects a chord, it splits it in two parts, in two equal parts. So a diameter bisects a chord. So if I know that the entire length of that diameter is 10, I'm going to say, or sorry, that chord is 10, this is going to split it in half. So both sides of that diameter are going to be 5. So assuming that this one is the same, both sides of where this piece is measured to the center are going to be 5 units as well. So what I've ended up with here is a right triangle with a missing side. So if I have a right triangle with a missing side, I use the Pythagorean theorem. So that's a squared plus b squared equals c squared. So the hypotenuse of a right triangle is always across from that right angle. So 6 is going to be the hypotenuse. And then these two things are going to be the side lengths. So it says that if two chords are congruent, then they are equidistant from the center. I'm going to go in and copy that x down here. So one of those legs is x, and the other leg is 5 of that right triangle that we've identified. So looking at this right triangle that's created with the radius and that chord and the distance. So I'm going to go through and solve this. So x squared plus 25 equals 36. I'm going to take 25 from both sides. So 36 minus 25 is 11. And then to figure out what x is, I'm going to take the square root. And so x equals the square root of 11. I always check to see if there's any direction. So since this one did not tell me how to give my answer, this is the exact answer. It also might have told me to round, and if it did, then I would find an estimate. So the estimate can be rounded to whatever decimal place they tell you. They didn't tell us here, so I'm just providing this as an example. If it had said round to the nearest tenths, then this would be about 3.3 units. So it's about 3.3. The exact answer is the square root of 11, but the approximate answer would be 3.3. So that's how we can use these arc, tangent, and chord theorems to solve some problems with